The first is from Vikrant at Fluent.ai. So Vikrant, over to you.
Thank you, Ian. Thanks everyone for being here. I'm going to talk about the work Fluent team has been doing in neural architecture search for bringing speech recognition to very low power devices with new functionalities. Before jumping into neural architecture search, let me set the stage by providing some background. So what do we mean by what kind of devices we're targeting? What do we mean by low power devices? So the kind of devices we're targeting are like a remote control or a wristwatch, which run on very low power platforms and also have to run on batteries for a long amount of time. In terms of the enhanced functionalities we're talking about is to bring more natural voice user interfaces, to bring some of the unique work that Fluent team has been doing in ASR-free end-to-end spoken language understanding, which means that there's no text output in the system and the system is able to directly extract meaning from the incoming speech. And this allows us to create systems that are more nimble, more able to provide functionality such as multilingual speech recognition on small devices. The table at the bottom of this slide, it highlights some of these, some of the models that our team has developed. So for example, we have single wake word models that are only using 22 kilobytes of RAM, 26 kilobytes of RAM, and we also have multilingual command models that can run in as little as 20 kilobytes of RAM and uses 10 millions of operations per second. Before going further, let me give you a quick demo.
Computer, hello. Now change screen red in Mandarin. Alexa, 把屏幕改成红色. Now make screen blue in Korean.
컴퓨터, 화면 파란색으로 바꿔. Alexa, start flashing the screen.
So what we saw here is a very low power platform.
Excuse me, Vikrant, sorry to interrupt. Unfortunately, when you play the video, the audio does not go out to the audience. So just so you're aware of that, you may want to repeat that and just use your own words to talk about that. Your computer audio does not go out.
Okay, thank you. So this is a demo. Basically, I'm going to speak out what they're saying. Computer. Hello.
Now change screen red in Mandarin.
Changing screen red in Mandarin by providing a Mandarin command.
Now make screen.
I can't say Mandarin, so I'm gonna pause.
화면 파란색으로 바꿔.
And also changing screen to blue in Korean. So this model basically has three languages: English, Mandarin, Korean, everything running on this low power device, and three parallel wake words. Also, the device is listening for computer, Alexa, and Hey Google, everything in parallel. Everything is happening on this device. So this is the kind of user experience or enhanced functionality I'm talking about, right? So that's the background. With that, let's jump into neural architecture search. So neural architecture search is basically a AutoML approach, right? And in simple terms, it's neural network designing other neural networks. If you think about it, most of the neural architecture search approaches could be divided in two broad categories. There are search or exploration in big search space without any hint, and they can be very time consuming. Or there are methods that learn or start from an expert design structure and then build from there. However, these methods could be limited in their domain of exploration or in the type of structures they can discover. What we set out to do in this work was to design an algorithm that could learn from expert design structures, but at the same time freely explore the search space to come up with new architectures. And if you think about it, most AutoML algorithms, even random search, can find good architectures if we have infinite amount of time. But that's the thing, we don't have infinite amount of time. So with that in mind, we came up with the objective of an ideal NAS algorithm, which is to discover a higher number of well-performing neural architectures in less amount of time, right? So we want to find better architectures faster and more of those as well. So with that, we designed GNASIL, guided neural architecture search with imitation learning, right? So GNASIL is a method that greedily designs a new neural architecture layer by layer. and it takes advantage of, it has an RL agent, which is soft actor critic combined with hindsight experience replay that allows it to create us to get more sample efficient solutions and faster optimizations. GNASIL also takes advantage of expert designed architecture, so called using imitation learning, and it keeps a dictionary of all the discovered architectures or neural structures and uses those in combination with the learning from the RL agent to decide upon a new architecture layer by layer. The reward for function in this case is the accuracy as well as the floating point flops, right? So we want to design new architectures that stay within certain computational complexity because we're targeting tinyML devices here. So with that in mind, let's jump a little bit deeper into this, right? So let's say here on the left-hand side is what my input state is. So in this case, you have a network that has certain number of layers, let's say L1 and L2 defined, and you want to grow this network to provide better accuracy. We always have an L out layer because we want to evaluate the intermediary architectures as well. So we feed the current state into the entire guided GNASIL agent. Then based on previous learning as well as imitation learning, the RL agent would suggest some new layers to add. The planning options also based on previous learning would from the network dictionary would suggest certain options as well. Then these options are evaluated. So typically we put a beam width of 5 different options to evaluate at certain stage and choose the best performing architecture at that stage, right? So we're greedily choosing the architectures, and then we save these into the experience replay memory for the RL agent as well as into the network dictionary for the entire GNASIL agent. And the output here could be one layer, or in the next stage it could be one layer. It could even be multiple layers. And the reason for multiple layers is that it helps us to design the network faster or grow the network faster. And we found in our experiments that actually even by using multiple layers, we were able to reach very good optimal solutions. Sorry. Okay, so how did we evaluate these systems? We evaluated these on an openly available data set called Speech Commands from Google. This is a keyword spotting task for speech recognition, contains about 65,000 recordings of 30 commands. Some of those commands, 10, were taken as the keywords we wanted to detect, and 20 as the filler words that we wanted to reject. This is a fairly standard setup for this task, and many papers in the literature also cover this similar setup. So what did we compare? Because we wanted to see some of the work done in literature as well as the importance of learning versus imitation versus planning and their various combinations. So we compared the outcome with the expert design structures as well. So the table here on the left-hand side, it shows the top row here, shows the expert design architecture and its accuracy on this particular task. And then the other row shows GNASIL and some other architectures that we design either replicating from literature or just on our own that takes only certain components out of GNASIL, either learning or imitation or planning or a combination of those. And on the right-hand side, we have this graph, and it's a bit complicated, so let me walk through it. So what we want to pay attention to is these black circles, which is a expert design architecture. So it gives very good accuracy and has a low footprint in terms of the computational complexity, which is the flops here on x-axis, right? So the experts spent a lot of time designing this architecture. And then if you look in terms of what we want is an architecture or a neural architecture basically that gives very high accuracy at low footprint. And in that sense, we have these red dots here as well as these blue dots that gave us good accuracy. The red one referred to GNASIL and the blue one referred to GIL. Comparing these two, we see the GNASIL one is very close to the expert design architecture, which is also visible here in the table by comparing the first two rows, as well as we see that GIL, which contains imitation and planning, but no learning. There's no RL agent in this case. It is able to reach almost the same accuracy, but at a higher computational complexity. Also, for a given amount of time, GIL was only able to find 15 architectures as opposed to 25, which these comparisons are based on first 25 discovered architectures. So the key takeaway here is that GNASIL is able to find a higher number of architectures at low footprint. The other analysis we did, again, to further compare learning with imitation, with planning, to see the quality of discovered architecture. So if each one of these algorithms designed 25 architectures, except GIL, which was only able to design 15, what is the overall quality of those architectures? So if you look at these plots here on the right-hand side, these are histograms of with accuracy on the x-axis and how many architectures or structures fall within a certain accuracy bin. So if we look at, for example, let's look at our NAS, which is our implementation of NAS. It includes learning, but there's no imitation or planning. So you see that it did discover a number of architectures, but they were not very well performing, and most of them averaged around here between 40 to 60. Then similarly for randomness, we see the same pattern, and this is also visible here by looking at our NAS and random NAS in these tables. If you look at GNASIL, it did this GNASIL, sorry, here right on the top, it did discover 25 structures, and all of them were performing very well, or most of them were performing about very well. So here, this is one of the key characteristic that we wanted to maximize, right? So as I said, the objective in the beginning was to find higher number of well-performing architectures faster. And so GNASIL was able to do that. As I said, GIL is able to find good performing architectures, but without the RL agent, it's not able to design new architectures. It was only able to find 15 architectures that performed fairly well, but still less novelty than what GNASIL was able to find. And this is similar pattern across different combinations of learning and planning. So what we see from here is that learning, when combined with imitation and planning, really is what gave us the best result in terms of our preset objective criteria. So conclusion, we have a unique end-to-end spoken language understanding framework for speech recognition that allows us to design low power architectures and provide new functionalities. Our GNASIL is able to increase the speed and efficiency of search for low power architectures by designing optimal solutions with similarly learning from imitation learning as well as free exploration in a big search space. It is an early work. There's a lot to be done on GNASIL still. For example, it still takes a lot of time to find these new architectures. The beam width is something we are still playing with. Maybe we are pruning too early for some of the architectures, so maybe the greedy method is not the best way. So there is a lot of future work there that we're undertaking on this. So that's all in terms of related to this work. As a side note, we are actively hiring for senior speech scientists, and you could apply on our website. Thank you.
All right, thank you, Vikrant. That was a very interesting talk. Folks, please put your questions in the app. So while those questions come in, I have a question for you, Vikrant. So you mentioned that you had some internal designed expert networks for this use case, and then you had the comparison of GNASIL or compared to those expert networks. When creating your RL framework, did you use that expert knowledge such that, as part of the search space, that you're going to search some of those expert components from that expert network in the RL search space?
So the GNASIL can take multiple expert structures, and the first phase of overall training is to teach the agent by building those structures. Right. So step by step, we go through. Let's say one of these structures was a mobile net. So the agent learns to build mobile net. What are the good selection criteria for that?
And so you used your in-house expert network as part of that.
Right. Yeah.
Okay.
Yeah.
And do you think it would still achieve decent results if you'd started from maybe a less optimized network?
Right. So this is what is visible in this table, right? So if you look in this table, there are the GNAS option and our NAS option. They do not have any imitation, and in this case, they are they're not able to perform as well, right? So the average accuracy for both of these are much lower, and even the maximum accuracy, it's able to maybe reach there for in terms of maximum accuracy, but for GNAS, you will see the most of the distort architectures are not performing as well.
Yeah. Okay, got it. Thank you.
So it's the quality of the distort architectures. So good.
So another question that's coming in: what is the model size of your GNASIL based model?
So the cap here, if you go back here, was we measured previously. We had measured in terms of the number of parameters, but what we found later, especially when implementing on tiny devices, that more than the number of parameters, the exact implementation of those, and therefore the actual number of operations is more important. So we put a cap at 25 here in megaflops. And most of these structures are like the hand design structure is about 15, and the GNASIL Discord structure is a little bit larger than that.
Okay, great. Thank you.
I'd like to acknowledge our sponsors. First, it's ARM that develops software and hardware for tinyML. Qualcomm, Samsung. These three are the executive sponsors. And then followed by platinum sponsors: ETA Compute, Lattice Semiconductors, and the gold sponsors are BrainChip Corporation, Cisco, DSP Group, H-Impulse, EMSA Visual Sense, General Matter Labs, Green Waves Technologies, Hymex, Imagimob, Latent AI, Maxim Integrated, Kixo, Reality AI, SenseML, Silicon Labs, Sentient, and Google TensorFlow. XMOS, and the silver sponsors are H-Cortex, HOTS, and SynSense. Again, we are very grateful for their continued support, and this is a great testimony that the foundation and this community is really of huge interest for the companies and for the whole world.